Ramesh, Vamsi. Okay. So good morning, guys. Yesterday we were seeing this biofuel, okay, and I'm left with biofuel policy, okay. So keep a heading as biofuel policy, and then we'll start a new topic which is nuclear energy, okay. It's a really important topic, but before that, keep a heading as biofuel policy, biofuel policy, okay. Fine. It was came in 2018. It was came in 2018. Okay. So when it was came, okay, at that time we are not using that much of ethanol in the petrol, which means we are not blending that much of ethanol in the petrol. We used to blend around 8.5% before 8.5% of ethanol. 8.5% of ethanol in 8.5% of ethanol in petrol, which means 8.5% will be ethanol plus how much? 91.5% will be petrol. Okay. Now we have set a target, and in the target, what we have achieved is by 2022. By 2022, okay, we set a formula that E10, which means by the year of 2022 we need to mix 10% of ethanol in, which means, see, blending is quite simple, but after blending the fuel has to work in the internal combustion engine. So if it has to work, we have to develop a technology. So by 2022 we have set up target wherein our internal combustion engines, IC engines, will work with 10% ethanol plus 90% petrol. Before we don't have the technology. Before maximum 8.5% ethanol. Later by 2022, what we have done, we have made some minor changes in our engine, okay, and in the engine we have made changes and we achieved 10% ethanol blending, okay. And in the same policy, what we have done is by 2025, which means this year, okay, our formula is E20, which means 20% ethanol plus 80% petrol, okay. So now, I mean, in this year our engines are going to modify, and those engines will be capable of running a fuel which contains 20% ethanol plus 80% petrol. Understood? Right on. So this is our biofuel policy. Before we used to blend around 8.5% ethanol. By 2022, we have set a target saying 10%. And now by 2025, 20%. How ethanol is made? Sugarcane and maize seeds. From the maize stem, what will produce? Biodiesel. From maize seeds will produce ethanol. See here, if you can see, the quality of E20 is better because here 20% ethanol is there, which means anti-knocking agents are more here. So knocking will be less in the fuel. So it will give you more heat. If sound is more, heat will be less. If sound is less, then heat will be more. Okay, so this is all about petrol. And we have another fuel which is diesel. So for diesel, what is our biofuel policy is by 2030. By 2030, we are planning to blend 5% of biodiesel. Diesel. So yesterday we have seen, yes, biodiesel. That biodiesel we are planning 5% to blend with diesel. Okay, by 2030. Okay, now write down. Ultimate target of our biofuel is ultimate target of our biofuel is hyphen reduction of up to reduction of up to 20% of fossil fuel imports by 2030. So our ultimate objective is now we are, let's say, we are importing 100% and we are spending $100 on that. Okay, this is from our forex reserves. Forex reserves. Now our plan is, what is our plan? By 2030, we need to reduce this imports by 20%. Then we'll consume only $80 and remaining $20 we'll use on other developmental projects. Okay, so this is the ultimate goal of this biofuel policy. Biofuel policy, only two things. For petrol, before we used to use around 8.5%. By 2022, we achieved 10%. And by 2025, this year we are going to achieve 20%. Okay. And for the diesel, by 2030, 5% biodiesel will be blended with the diesel. Okay. And our ultimate objective is reduction of 20% fossil fuel imports by 2030. Simple. Okay. Now, there is a term which is associated with it. Write down. Flex fuel vehicle. Flex fuel vehicle. Flex fuel vehicle. Flexibility option of fuel. Flexibility option of fuel. Flexibility option of fuel. Now what is this? Let's say by 2025 our plan is E20. Now let's say government designed a engine wherein this 20% blended ethanol will be used. Okay. Now let's say initially what happens in the major cities, only this fuel will be available. In the remaining cities, again 10% fuel will be available. Now in the major cities, let's say you have filled the petrol and you have went to another city. Now in that city, there might be chances you won't be getting this E20 fuel. Yes, obviously, I mean, just now changed, right? So still there are chances that E10 fuel only available because, I mean, all the other vehicles which are, I mean, old vehicles which are having a technology of E10 fuel only. Yes. Now, just because you have bought E20 vehicle, it doesn't mean all the petrol bunk suppliers will supply E20 only. They'll supply still E10. Yes. Let's say, let's say two persons, Vamsi and this Ramesh. Okay. Vamsi, he has bought in 2022, he have bought a vehicle. And this Ramesh, he has bought a new vehicle. He's going to get a vehicle in 2025. So in this vehicle, the fuel it is going to use this E20, and in this vehicle the fuel it is going to use this E10. Okay. So now it is 2025. So all of a sudden we have changed from E10 to E20. Okay. Still there are some old vehicles, right? Almost 90-95% vehicles are old vehicles only. They need E10 only. So generally majority of the fuel supplied will be E10 only, but still E20 outlets will be there. Okay. So now this Ramesh vehicle, what happens here is this will work on E20 as well as E10 also. E10 also. This is called as flex fuel vehicle. Whenever you are changing to a new technology, there it is involved a flex fuel vehicle, which means there will be a flexibility of fuel option. It will be running with E20. If not E20, it will run with E10 as well. Understood? Yes? Right on. Done? If you want, you can write down that example as well. Done? Understood? Yes. So biofuel generations we have seen first, second, third, fourth, and then biofuel policy. So everything is clear? Yes? Okay. Now, new topic, nuclear energy. Nuclear energy. In your chemistry, there is a chapter called periodic table. Yes? How many elements will be there in the periodic table? Okay. So 188 in 1990s. Later it changed to 112 and now it is 118 it seems. Okay. So still when I was reading it is 112 but now it is 118. Okay. So to learn this topic, trust me, you need chemistry. So for 10 to 15 minutes we'll revise the chemistry topics. Okay. I'll say revision only, but for you it is basic learning. Okay. So keep a heading as basics. Okay. So just now I have told you in the chemistry, the basic unit is atom, and people will call it as element as well. Okay. And again, atom has proton, neutron, everything will be there, electron. Okay. But the thing here is, okay, we'll consider this as our basic unit. Okay. So our basic unit is atom or element. Okay. So how many elements are there? 118. These all these elements are not natural elements. These are both natural and derived. These are both natural and derived. Okay, right on. In nuclear energy, we'll use only three elements: uranium, plutonium, thorium. Okay, so here we don't need to learn all the 118 elements. Only three elements will be used here. Okay, uranium, plutonium, thorium. Okay, so uranium, plutonium, thorium. Okay, or else write down by this. Write down uranium, plutonium, thorium. Okay, so uranium, thorium, plutonium. Okay, see, this uranium it is natural, and this thorium it is natural. Okay, so uranium you'll get in uranium you'll get maximum in Australia. Where? Australia. Okay, and thorium you'll get maximum in India. Okay, in India, right? One more fact, this will get from pitch blend, and this will get from monazite soil, and plutonium will be maximum in nowhere, because it is derived. It is derived. Those are natural. See, there will be a material called pitch blende. Okay, in the pitch blende what you will find is uranium. Okay, similarly there is a soil called monazite soil in India. In the coastal areas, if you'll collect the soil, out of collected soil merely you'll find monazite soil. In that monazite soil you find thorium. You'll find thorium. So monazite soil is more in India. Similarly, pitch blende is more in Australia. That's the reason uranium is more in Australia, thorium is more in India. Remaining it is derived. How it is derived? See. Okay, I'll tell you. Actually, it is derived from uranium. Okay, I'll tell you a equation. Okay, that equation I'll write it down for 10 times in this class. Okay, after this class, you'll remember that equation forever. Okay, so write down here. Plutonium is derived from uranium. When you'll break down this uranium, there will be some waste particles left. That waste particle is nothing but plutonium. Okay, right now. Uranium, sorry, plutonium is derived from uranium. So understood? In the chemistry, we'll consider the basic unit is atom or elements. We have 118 elements. Out of 118, Some are natural and some are derived. Okay, here we'll read only three elements. One is uranium, plutonium, thorium. Uranium and thorium are natural, which means they will be derived. I mean, you'll get them in the natural form, just like pitchblende and monozoic soil. Okay, and this one plutonium is derived. How it is derived? When you'll break this uranium, okay, how you'll break, I'll tell you. Fission process, fusion process, everything I'll teach. Okay, when you'll break this uranium, there will be some waste. In that waste, uranium will be there, sorry, plutonium will be there. Okay, so understood basics? Okay, next. Right now, let's say I have taken a element carbon. Okay, so here it will be written something like this. Yes, what are these numbers? Atomic number, atomic mass. This is atomic number, and this is atomic mass. Okay, so what is atomic number? Number of electrons or protons. Number of electrons or protons. If the number is 6, which means this atom contains 6 electrons or 6 protons. Okay, so this is nothing but number of electrons or protons. Okay, and what is atomic mass? Protons plus neutrons. Protons plus neutrons. Now tell me, now tell me, here electrons or protons equals to 6. Protons plus neutrons equals to 12. How many number of neutrons are there here? 6. Understood? Yes. So here protons equals to 6, protons plus neutrons equals to 12. So obviously neutrons equals to 12 minus proton, which is 12 minus 6, which is 6. Understood? Okay, so here how many neutrons are there? 6. This is this will be there in the chemistry. Okay, when I'll deal chemistry, then I'll tell you all these things. But see, here the point I'm going to convey is different. If I'll add one neutron here, what am I doing here? I'm adding one neutron. Okay, now what will be the equation? 6 C 13. Okay, so here both are same, both are same atoms with same atomic number but different atomic mass, and these are called as isotopes. What are these called as? Isotopes. So this we are going to learn here. Isotopes. Isotopes means same atomic number but different atomic mass. Once the atomic mass is different, their properties will be different. Different properties. Different properties. Okay. So let's leave it to me. I'll explain everything. First write down this. After writing this, tell me, I'll tell you a note point. So in the chemistry, this neutron, you'll show it as 0 and 1. Okay. If you want to write it as N also, it is okay. But if you want to be more technical, then we'll write it as 0 and 1. Okay. When I say 0 in the down, which means 0 protons and 0 electrons. And when I say 1 above, protons plus neutrons, obviously protons are 0. So we are left with neutrons, 1 neutron. Okay. Done. So how many elements you know in this periodic table? At least 5, 6. What are those? Hydrogen, helium, lithium. Okay. Keep a heading as isotopes and write down isotopes. A element can be can be exist in more than one form. An element can be exist in more than one form. Okay, so these are same elements. Okay, see, this is carbon element and this is carbon element, same element but different forms. Okay, those different forms are nothing but isotopes. Okay, so to be like precise, if you want to talk about this, then same atomic number but different atomic mass. So whenever the mass changes, the properties will change, right? So what are isotopes? Okay, done. Now see, periodic table, periodic table. Okay, no worries, I don't teach periodic table here, only 3 elements we're gonna learn here. Okay, nothing else, but still we'll start with hydrogen, helium, lithium, beryllium, boron, carbon. Enough. Then we'll go to 82nd element. Okay, and then 83rd element. Okay, what are those elements? Not required. And then we'll go to 118th element. Okay, so what is that element? Not required. Okay, so why am I writing like this? See, before 84 the elements will not carry any radioactivity, but after 82, before 82 the elements are not radioactive elements. After 82, which means from 83, the elements are radioactive in nature. What is that? Radio activity is more. That's the reason we'll call these elements as radioactive elements. Radioactive elements. Okay, so we are going to learn about uranium, plutonium, thorium. Those are radioactive elements and which will be there in 1992 and 94. Okay, so what am I trying to tell you here is uranium, this plutonium and thorium, these are radioactive elements. Now the point here is, what is radioactivity? Radioactive means these elements are not stable. These elements are not stable. Whenever a particle is coming to it, immediately they'll react with them and they'll break. and when they are breaking, they'll give you more heat and energy. Understood? Whenever a particle is coming towards them, they will easily react, and they'll easily react, either they will form, combine, or they'll break. Even if they are combining or even if they are breaking, they'll produce more energy or heat, and this energy or heat will use to boil the water. And whenever we are boiling the water, we'll get steam. Whenever we are getting the steam, then we can run turbines. Whenever we are running the turbines, we'll get mechanical energy. Whenever we are getting the mechanical energy, we'll get dynamo in place, and this dynamo will convert that mechanical energy into electrical energy. Understood? So radioactive elements, fine, right on. Okay, done. Now see, we are going to read about this uranium, thorium, and plutonium. Okay, so first we'll know their atomic numbers. Okay, so actually thorium comes first 90, and then increase to 92, so you'll get uranium, and then increase to, you'll get 94. So uranium is 92. The byproduct, I mean the waste of uranium, comes after. First we'll let the uranium to break down, then only the waste will come out. So obviously uranium will come first, and then plutonium will come after. Okay, before that, we are Indians, so we are always number one, so this will come first. Okay, and tell me, see, in class 12th or class 10th, I think. Okay, so we'll read something like this. Let's say this is atom. Okay, in the atom center will have nucleus. In the nucleus will have neutrons plus protons, and electrons will be rotating around nucleus. Okay, let's say if it is hydrogen, then only two electrons will be there and two electrons will be rotating. If it is higher elements, then here some 8, some 10. Similarly, SPDF. Okay, similarly, if the atomic number is more, then the atom size will be, see, if the atomic number is less, okay, atomic number is less, then the atom size will be less. If the atomic number is more, atom size will be more. Yes, when the atom size will be more, inside nucleus size will also increase. Okay, so here what am I trying to tell you is these particles are large atomic size and large nucleus. Okay, right on. This uranium, plutonium, and thorium are large type of atoms, are large type of atoms. In bracket write down large atomic size large nucleus. Uranium, plutonium, thorium are large type of atoms. Large type of atoms. In bracket write down atomic size is large atomic size, comma, large nucleus. Large nucleus. Understood? Okay. Now we'll get back to our basic chapter, which is nuclear energy. Okay. So nuclear energy, generally two reactions will be there. One will call it as nuclear fission and second one is nuclear fusion. So first we'll see fission. Right now. Nuclear nuclear fission. Okay. Alright. Breakdown of breakdown of large size of atoms. Breakdown of large size of atoms or nuclei or nuclei into small size of atoms or nuclei. A breakdown of large size of atoms or nuclei into small size of atoms or nuclei is called as nuclear fission. Okay. So see here, if nuclear fission has to happen, then what is the initial condition? The atom must be of large size. Okay, and these are large sized atoms. So nuclear fission will happen only in these items, not in the small items. In the small items, what will happen is nuclear fusion. Okay, understood? Now, the energy generated in this process is called as the energy generated in this process is called as the energy generated in this process is called as fission energy. Fission energy. Okay, write down a reaction. So this reaction is really important. Okay, so uranium atomic number 92, 90 is thorium, 94 is plutonium. Okay, so I've told you this is a radioactive element, which means this is not stable. Whenever it reacts with any other elements, immediately it will break down. Okay, so highly reactive. Okay, so here I'm taking a neutron. Okay, and immediately it will react because this is a radioactive element. Okay, so while it is reacting, okay, what happens here is it will produce barium plus krypton. 56 plus 36, 56 plus 36, 92 plus 3 neutrons it will produce plus heat it will produce plus waste it will produce. Simple. Uranium, it is highly radioactive element. So whenever it will react with a element, immediately it will react and it will break down. So here what's happening here is it is reacting with a neutron and immediately it is breaking down into barium and krypton. Barium and krypton. Plus 3 neutrons. Why these 3 neutrons? I'll tell you in the moderator. Okay. So 3 neutrons. Okay. And then what happens is it is producing some heat and then waste. So out of waste, what we will get? Plutonium. And this heat is called as fission heat. Okay, write down this reaction. Trust me, this reaction, only this reaction is there in your nuclear energy chapter. Okay, if you can by heart this reaction, your work will be done. Done. Now write down examples. 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 Atom bomb. Examples. Atom bomb. Atom bomb. Nuclear Energy Development Program of India. Nuclear Energy Development Program of India. Nuclear Energy Development Program of India. Nuclear Energy Development Program of. Okay. Then nuclear fission. Okay. So trust me, this also we are learning from childhood, but we never understood anything. But this is the time. See, large atoms will be divided into small atoms. Okay. And the small atoms, whenever it is dividing into small atoms, it will produce some energy or heat. That heat or energy is nothing but fission energy. Okay. And we have taken equation which is uranium. Whenever it is reacting with a neutron, what happens is it will produce barium. Okay, so these are small atoms. These are small atoms, because see, I mean 92, and here it is 56 plus 36, which means small atoms. It is dividing into small atoms. Whenever it is dividing into small atoms, it will produce some heat, and this heat is nothing but our. Okay, now see, I mean people will say, I mean this is a continuous reaction, you cannot stop the reaction. Why? See, whenever uranium, again I'll repeat this. Okay, whenever this uranium is reacting with a neutron, okay, what it is producing? Barium, krypton, plus 3 neutrons plus some energy. Okay, so leave it, this energy will be converted into electricity. Okay, so leave about this. Now see, it is not the case like we are taking only one uranium. No, right? We'll load some 1,000 kgs of uranium into the plant, and then we'll start the reaction with one neutron. So now what happens is one neutron will enter into the picture, and it will produce 3 neutrons. Now these 3 neutrons, now they'll go to 3 uranium particles. Now this 3 and 3, they'll produce, understood, 9 neutrons. Now this 9 neutrons, again they'll produce 27 neutrons, and the process will be on one side, the process will be more, the heat generated will be more. Initially only one uranium is splitting, so only one, let's say one energy is coming. Okay, so initially what's happening is one uranium is splitting and one energy only we are getting. Second time we have 3 neutrons. Now these 3 neutrons will react with 3 uranium. So here 3 uraniums are there. Now they will produce 3 calories. Let's say a unit of energy is calories. So 3 calories it will produce. Next time we have here 9 neutrons. 9 neutrons will go and it will react with 9 uranium particles. Now 9 uranium particles will produce 9 calories of energy. On the other side, it will produce 9 3 is 27. 27 neutrons. Now 27 neutrons will come and react with 27 uranium particles. Now 27 calories will produce. And 27 3s 81. Now 81 uranium particles will go and neutrons will go and they'll react with 81 uranium particles. Now the energy produced here will be 81 threes 243. So again 243 neutrons will produce. That's the reason this is highly powerful. Understand? Yes? So this is the importance of these 3 neutrons. Okay? Initially the process will be slow. All of a sudden the process will be increased and the heat produced will be high. Understand? Yes? That's the reason we'll use inside there is a thing called control rod. Okay? We'll see everything. Okay? In this chapter we'll cover everything. Understand? If we leave it like this, then it will produce more heat, more heat. Understood? Yes? Okay. Now, another topic which is nuclear fusion. Nuclear fusion. Okay, right now. Here, what will happen? Small size of atoms will fuse together and form a large size of atoms. Okay, right now. Here, two small size atoms, two small size atoms fuse together to form a large size of atom. Fuse, F-U-S-E. Here, two small size atoms fuse together to produce one large size particle, large size atom. Next, the energy generated in this process is called as fusion energy. Fusion energy. Okay, see, this is a small particle and this is a small particle. Whenever they'll fuse, okay, a large particle will be formed. Along with the large particle, what will form? Heat or energy, and this is called as fusion energy. So example write down, I mean not example, equation write down. 1H2 plus 1H2, these two particles will combine and they'll form 2 helium 4 plus energy, and this energy is nothing but fusion energy. Okay, so the energy which we are getting from sun is nuclear fission energy or fusion energy? No, fusion. Okay, so in the sun what happens is two hydrogen particles will react and they'll produce a helium particle, and along with that energy will come. So the energy of sun is an example of fusion energy. So in the energy, I mean sun energy, what will happen? I mean from the childhood we are learning this. One hydrogen particle will react with another hydrogen particle and it will produce helium particle. And that's how some energy will come. This energy is nothing but solar energy. Okay. Done. Write down examples. Solar energy, hydrogen bomb. Write down solar energy, hydrogen bomb, and artificial sun experiment. Artificial sun experiment. I mean, these days we are learning, I mean, reading about the stories, right? China is making an artificial sun. What it is making, it is simply reacting to hydrogen particles, and that's how you'll get a helium particle. Along with helium particle, you'll get some energy. That energy is nothing but solar energy. If the same process, if you're doing artificially, then it is called as artificial solar experiment. Understood? So examples are solar energy, hydrogen bomb, and artificial solar experiment. Now we'll compare these two things. Right now, nuclear fission versus fusion. Nuclear fission versus fusion. Nuclear fusion versus fusion. Okay. Fusion. Okay. So in the fission, see, obviously from the sun only we'll get more heat. So obviously in which process you'll get more heat? Fusion. So here less heat, and here more heat. Okay. First point clear. Second point, see, in the fission reaction I have written waste here. In the reaction you'll get some waste, nuclear waste. But nowhere in the fusion reaction I have mentioned the waste, which means in the fission you'll get nuclear waste. It will generate nuclear waste. And here no nuclear waste, no nuclear waste. See, both are uncontrollable, but somehow by using control rods and other stuff, we can still control the fission. Okay, so controllable, difficult but controllable. But this is uncontrollable. That's the reason. Okay, sun is giving you sun energy, I mean solar energy, since so many days, and it will give you for ever. Only because fusion and the reaction is uncontrollable. This is also uncontrollable, but still we'll use some technologies, then we'll control the process. But that is uncontrollable. No technology for that. Okay? Understood? Fine. Now keep a heading as Nuclear Development Program of Nuclear Energy Development Program of India. Okay? So I mean these two concepts are more than enough to learn about our Nuclear Energy Development Program of India. Keep a heading. Nuclear Development program of India. Who is the contributor? Homi Baba. Dr. Homi Baba. Okay. So contributor Dr. Homi Jamshed Baba, I think. Okay. Baba. Dr. Homi Baba. Okay. So write down. Dr. Baba. Dr. Baba made three stage nuclear energy program of India. Made three stage nuclear energy program of India. Okay. Now I'll give you some facts. Okay. So just note down the facts. Later I'll give you break and then come back. I'll teach you the concepts. Okay. So keep a heading as first stage. In every stage, we'll find four things. Okay. Fuel, moderator, coolant, reactor. In every stage, we'll find these four things. Okay. See, in the first stage, we'll find fuel as uranium. In the second stage, we'll find plutonium. And in the third stage, we'll find thorium. Simple? Right down. Okay. And the moderator and the coolant are heavy water. Heavy water, D2O. Okay. And the reactor is pressurized heavy water reactor. Pressurized, pressurized heavy water reactor. Pressurized heavy water reactor. Okay. See, intentionally I'm going slow, okay, because I mean all these concepts are quite new for you, and maybe you have read all these things in your class 6th to 10th, but trust me, you won't remember anything. That's the reason I'm going a bit slow, because chemistry is a bit confusion, and people will feel like this is quite difficult. So I'm going a bit slow. Fine. Now we'll enter into stage 2. Second stage. Again, here also we'll find four things. See, when I say fuel, okay, before what we have done is we have burned the fuel. We have burned the fuel. That's how we got the energy. But nowhere in the nuclear energy we are not burning the fuel. Instead, what we are doing, we are breaking down the fuel. We are breaking down the fuel. That's how we are getting the energy. Here we are not burning. What we are doing here, we are breaking down the fuel. Before we used to burn the fuel. Here we are breaking down the fuel. So here fuel is nothing but uranium, plutonium and thorium. Fuel, and then we'll find moderator and then coolant, reactor. So fuel is plutonium, and moderator generally you won't find here. Okay, why? I'll tell you the reason when I'm discussing this moderator. Okay, and the coolant is liquid sodium. Okay, and the reactor is breeder reactor. Breeder reactor. No worries, everything you'll understand. Okay. Next, third generation, third stage. Then this. Okay, these are facts. I mean, directly they'll ask you. In the second stage, what is the coolant? What is the coolant? Liquid sodium. And if they'll ask you about reactor, breeder reactor. Before, pressurized heavy water reactor. Done? Now, third stage. Third stage. Here also we'll find four things. First one is fuel, moderator, coolant and reactor. Okay. See, fuel is thorium. Moderator is light water. Light water. And we'll call this light water as demineralized water. Okay. Demineralized water, which means from the normal water, we'll take all the minerals. We'll take out all the minerals and we'll call this as light water. And this is also called as demineralized water. Coolant is heavy water, D2. And the reactor is here both the reactors will be used. AHWR, advanced heavy water reactor. The first one we have seen is pressurized heavy water, and this is advanced heavy water reactor or breeder reactor. So these are the stages. Okay, so first stage, second stage, and third stage. Okay, so let's have a quick revision. In the first stage, what is the fuel? Uranium. Moderator and coolant are both same, heavy water. And then we have seen reactor, pressurized heavy water reactor. Second stage, fuel, plutonium. Okay, and here you won't find moderator. Okay, you'll find coolant here, and the coolant is liquid sodium. Okay, and the reactor is breeder reactor. Third stage, thorium. And here the moderator is light water or demineralized water. Okay, and then coolant is heavy water D2O, and then reactor is advanced heavy water reactor or breeder reactor. Okay, fine, simple. Okay, so now take a break for 15 minutes. Okay, and then we'll continue with the what is fuel, moderator and coolant. If possible, reactor also today I'll discuss. If not the case, next class. Okay, chalo then, take a short break.